Imagine a world so distant, so quietly drifting at the edge of our solar system, that it was mistaken for a star for centuries, suspended in the profound darkness, wrapped in layers of freezing gases. Uranus hangs like a pale blue marble against the velvet black of space, a world that feels almost dreamlike, serene, and yet profoundly unsettling in its mysteries. This isn't just another planet, it's the solar system's great enigma, an ice giant that challenges everything we think we know about how planets form and behave. When Voyager 2 swept past it in 1986, humanity caught its first and only close-up glimpse of this strange world, a fleeting visit that lasted mere hours but left us with decades of unanswered questions, each more baffling than the last. From its bizarre sideways spin, as if knocked over by some colossal ancient impact, to its faint, complex ring system and an array of moons that seem to defy natural logic, Uranus is a celestial rebel. It doesn't play by the rules. Its atmosphere swirls with mysteries. Why does it radiate so little heat? What drives its extreme seasons, each lasting over 20 years? And what secrets lie buried in its deep, supersonic ocean, a form of water so strange it behaves like both a liquid and a solid? For all its calm and quiet beauty, this world is whispering puzzles that scientists are still straining to decode. But what if we told you that the story of Uranus is only beginning to unfold? In this video, we're setting off on a journey to explore the 25 greatest unexplained mysteries of this captivating ice giant. From its chaotic magnetic field that tumbles wildly off-center to the possibility of hidden oceans beneath the surfaces of its moons. We'll revisit the tantalizing clues Voyager 2 left behind and dive into the bold missions that might one day unveil the truths lying in wait within this frozen realm. So come with us as we venture into the unknown, question what we think we understand about our cosmic neighborhood, and uncover why Uranus remains one of the most compelling and mysterious worlds ever discovered. Our journey into the unknown begins with the most glaring oddity, the feature that sets Uranus apart from every other world in our solar system, its extreme axial tilt. While Earth is gently tipped at about 23 degrees and most other planets lean at angles you might expect, Uranus is lying almost completely on its side, spinning with its north pole pointed nearly directly at the Sun. This 98-degree roll transforms it from a mere planet into a cosmic peculiarity, a top spinning on its edge in the void. The immediate and most dramatic consequence of this bizarre orientation is a seasonal cycle of almost unimaginable extremes. Picture this as Uranus makes its 84-year-long journey around the Sun. Each pole endures 42 years of unbroken, brutal sunlight, followed by 42 years of absolute frigid darkness. The concept of a simple day-night cycle is utterly meaningless here. The entire climate of the planet is dictated by which hemisphere is bathed in light and which is frozen in an endless night. So, what colossal force could have knocked a planet of this size onto its side? The prevailing theory points to a violent, chaotic beginning. Scientists hypothesize that in the early, formative years of our solar system, a young Uranus was struck by a protoplanet, a massive, embryonic world roughly twice the size of Earth. This wasn't a glancing blow, it was a direct, cataclysmic impact that likely vaporized the impactor and fundamentally reshaped Uranus's very structure. The force of such a collision would have been enough to literally tip the entire world over, setting it into its peculiar sideways spin. This event may also explain another of the planet's mysteries, its surprising lack of internal heat. A giant impact could have essentially knocked the planet's core off balance, disrupting its internal engine and causing it to lose much of its primordial heat to space, leaving it significantly colder than its fellow ice giant, Neptune. Yet, this collision theory, while compelling, is not the only idea on the table. some researchers propose an alternative, suggesting that gravitational interactions with a massive, now lost moon or perhaps even a nearby giant planet in the unstable early solar system could have gradually torqued Uranus over immense spans of time. This gravitational tug-of-war would have been a slower, more graceful tipping rather than a single violent event. Each theory presents its own set of questions and implications, making the mystery of Uranus's tilt a fundamental puzzle that reaches into the very heart of planetary science. It forces us to question our models of how solar systems form and evolve, reminding us that the history written in the orbits of planets is often a story of incredible violence and profound chance. This profound chill leads us directly to our next great puzzle, the missing internal heat of Uranus. While most giant planets, including our own Jupiter and Saturn, radiate more energy into space than they receive from the Sun, a clear sign of a hot, active interior burning with leftover heat from their formation, Uranus behaves completely differently. It's a cosmic paradox. This world, closer to the Sun than its sibling Neptune, is almost perfectly in thermal equilibrium. The feeble warmth it emits is nearly equal to the tiny amount of solar energy it absorbs, making it the solar system's only giant planet that isn't generating a substantial amount of its own internal heat. This isn't just a minor discrepancy, it's a fundamental violation of our expectations for how a planet of its size and age should behave. To grasp why this is so strange, consider Neptune. It's significantly farther from the Sun, existing in a much colder region of space, and yet its core is pumping out immense heat, making its atmosphere far more dynamic and stormy than the relatively placid layers of Uranus. If both planets are thought to have formed in a similar way and are composed of similar materials, why is one a glowing ember and the other an ice-cold stone? Scientists are actively chasing several compelling hypotheses to solve this thermal mystery. One leading idea suggests that the same colossal impact thought to have tipped Uranus on its side may have also catastrophically disrupted its internal structure. The unimaginable force of a protoplanet slamming into it could have effectively scrambled its core, mixing dense, heavy elements upward and forcing lighter materials down. This event might have created a barrier, a kind of insulating layer within the planet that traps the primordial heat deep inside, preventing it from slowly rising to the surface and radiating away into space over billions of years. The planet's engine is still running, but it's muffled, its warmth locked away in a stratified interior. Another possibility points not to a single violent event, but to a quieter, more gradual process. Some models indicate that Uranus's interior might be structured in a way that severely limits convection, the large-scale churning of hot material rising, and cooler material sinking that drives heat transfer in planets. If the composition and density of its internal layers are just right, they could act as a planetary lid, suppressing the turbulent motions that bring warmth to the surface. It's as if the entire planet is wrapped in a celestial blanket. There's even a more exotic theory proposing that Uranus might have an unusual abundance of certain rocks or ices within its mantle that act as a powerful refrigerant, actively cooling the interior down. Whatever the true cause, this missing heat has a dramatic effect on the planet's weather and atmosphere. Without a strong internal heat source to drive powerful convection currents, Uranus's atmosphere appears much calmer and more uniformly frigid than the turbulent, stormy skies of Jupiter or Neptune. This energy deficit paints a picture of a world that is not just physically tilted but thermally dormant, a silent giant holding its secrets close and cold. If the planet's internal coldness and sideways spin weren't puzzling enough, our next mystery ventures into the truly bizarre realm of its magnetic field. When scientists first analyzed the data from Voyager 2, they discovered that Uranus doesn't just play by a different set of rules, it seems to have written its own rulebook entirely. Unlike Earth, which has a magnetic field that emerges from its poles and is roughly aligned with its rotational axis, the magnetic field of Uranus is chaotic, tilted, and fundamentally broken. It's offset from the planet's center by nearly 1/3 of its radius and canted over at a jarring 59-degree angle. This means the magnetic North Pole isn't anywhere near the geographic North Pole. In fact, it's closer to the equator. To put that into perspective, if Earth had a magnetic field this skewed, a compass in Washington, D.C. would point toward the middle of the Pacific Ocean instead of toward the Arctic. The result is a lopsided and asymmetric magnetosphere, a protective bubble of magnetism that wobbles and tumbles wildly as the planet rotates, behaving unlike any other in our entire solar system. So what could possibly generate such a disordered magnetic field? The leading hypothesis points to the planet's internal structure, which is believed to be drastically different from the iron core dynamos of the rocky planets. Scientists theorize that deep within Uranus, under crushing pressures and extreme temperatures, lies a superheated, electrically conductive ocean. But this isn't water as we know it. It's likely a slushy, viscous fluid composed of water, ammonia, and other ices, a state of matter so exotic that it can generate a magnetic field as it churns and circulates. The key to the anomaly might be that this ocean is not uniform. It's probably confined to a relatively thin, spherical shell surrounding the planet's core, rather than filling the entire interior. This shallow nature, combined with the planet's extreme axial tilt, could force the magnetic field to be generated in a turbulent, unstable layer, causing it to emerge from an off-center location and at that strange, dramatic angle. It's a magnetic field born from a fractured, messy engine. The consequences of this magnetic oddity are profound, especially for any future spacecraft or, hypothetically, for any form of life. Because the field is so off-center and tilted, the magnetosphere of Uranus is highly asymmetric, stronger on one side of the planet than the other. As the planet spins on its side, this lopsided magnetic bubble gets dragged through space in a complex, corkscrew-like pattern. During its 84-year orbit, the orientation of this wobbly field relative to the solar wind changes drastically, leading to a magnetosphere that can completely reconfigure itself over the course of a single Uranian day. This creates an environment of immense complexity, with magnetic field lines likely twisting, breaking, and reconnecting in ways we are only beginning to model. It presents a monumental challenge for scientists trying to understand space weather around this distant world, and adds yet another layer of profound mystery to the ice giant that refuses to conform. Moving from the chaotic dance of its magnetic field, we find another elegant and delicate feature adorning the ice giant, its intricate system of rings. While Saturn's brilliant, icy bands are the jewels of the solar system, the rings of Uranus are their subtle, shadowy cousins, a set of 13 faint, narrow loops etched into the darkness. They are not easily seen. In fact, they remained completely hidden from Earth-based observers until 1977, when astronomers accidentally discovered them as Uranus passed in front of a distant star. The star winked on and off repeatedly, not just behind the planet itself, but behind these previously unknown dark rings. This revealed a system far more complex and delicate than anyone had anticipated, composed of particles as dark as charcoal, reflecting only a tiny fraction of the sunlight that shines upon them. This profound darkness is our first puzzle. Why are these rings so incredibly different from the dazzling ice that makes up Saturn's iconic features? The leading theory suggests a story of cosmic weathering and contamination. The rings of Uranus are likely made of water ice, much like Saturn's, but they appear to be covered in a thick, dark layer of organic material. This could be radiation-processed methane, similar to the substance found on its dark moons, or other carbon-rich compounds. Over billions of years, a constant barrage of radiation from the Sun and high-energy particles trapped in Uranus's magnetosphere could have baked this dark crust onto the icy ring particles, effectively turning them into tiny, orbiting cinders. Another possibility is that the rings are simply made of different stuff from the start, perhaps the remnants of a dark moon or a captured object that was torn apart by the planet's gravity. It's dusty, carbon-rich debris forever destined to circle the planet in these precise ebony bands. Their precise structure is a marvel of gravitational engineering. These narrow rings are incredibly well-defined, with sharp edges that seem to defy the natural tendency of such debris to slowly spread out and dissipate over time. The secret to their maintenance appears to lie with a set of tiny, shepherding moons. Two of the most important are Cordelia and Ophelia, which orbit on either side of the brightest ring, known as the Epsilon ring. These small moons act like celestial border collies, using their gentle gravitational influence to herd the ring particles and keep them confined to their narrow paths. As a ring particle drifts too far outward, the gravity of the outer moon, Ophelia, tugs on it, stealing its energy and causing it to fall back inward. Conversely, if a particle drifts too far inward, the inner moon, Cordelia, gives it a gravitational nudge, pushing it back outward. This delicate balancing act, a constant gravitational tug of war between these shepherd moons, is what prevents the rings from either collapsing into the planet or drifting apart into nothingness. It's a stunningly precise orbital dance, one that highlights the intricate and fragile harmonies that can exist within a solar system. Now, as we turn our attention from the dark elegance of its rings to the very air it breathes, we encounter a mystery that is literally written in the atmosphere's chemical signature. One of the most perplexing revelations from the Voyager 2 flyby was the startling and unexpected composition of the Uranian atmosphere. Like a cosmic chef who left out a key ingredient, Uranus appears to be missing something that all planetary models said should be there in abundance: ammonia. In the freezing cold of the outer solar system, we expect planets like Uranus and Neptune, the so-called ice giants, to be rich in water, methane, and ammonia. These volatile compounds are the fundamental building blocks of the icy materials that coalesced in this distant, frigid region. Yet when scientists analyzed the data, they found the upper cloud decks of Uranus were strikingly depleted of ammonia, especially when compared to its sibling, Neptune. This missing ammonia presents a fascinating planetary puzzle. Where did it all go? The most compelling explanation is that something is actively hiding it from our view. Scientists believe that the ammonia isn't truly absent. Instead, it has likely been dissolved into a deep, massive ocean of superionic water within the planet's interior. In this exotic state, under immense pressure and heat, water molecules break apart, allowing ammonia to act as an antifreeze, mixing into the liquid and effectively being scrubbed from the upper atmosphere where we can detect it. Another theory suggests that the atmosphere itself might be structured in a way that creates a cold trap, a layer so frigid that it condenses ammonia into ice crystals, forming a hidden cloud deck buried deep beneath the topmost layers of haze, completely obscured from our instruments. But the atmosphere had another, far more pungent surprise in store. While ammonia was hiding, another compound was found in its place: hydrogen sulfide. This is the gas that gives rotten eggs their unmistakably foul odor. If you could somehow take a breath near Uranus's clouds, which is of course a physical impossibility, you would be met with the overwhelming and suffocating stench of a billion rotten eggs. This detection is far more than just a fun fact. It's a crucial chemical clue that fundamentally distinguishes Uranus from the gas giants like Jupiter and Saturn. Those larger worlds have cloud tops dominated by ammonia ice, but the presence of hydrogen sulfide ice on Uranus points to a dramatically different formation history. This difference in atmospheric chemistry suggests that Uranus and Neptune formed much farther from the Sun than Jupiter and Saturn, in a region of the protoplanetary disk that was cold enough for hydrogen sulfide to condense into ice grains and become a primary building block. It's a permanent atmospheric record of the planet birth address, a fossilized clue that it originated in an even colder, more remote neighborhood of the early solar system before perhaps migrating inward to its current orbit. The very smell of Uranus, therefore, is a whisper from its deepest past, telling a story of where it came from and how the architecture of our entire solar system was arranged billions of years ago. Given its profound internal cold and vast distance from the Sun, you might expect Uranus to be a monotonous, frozen world, a placid ball of gas with little happening in its atmosphere. Yet, when it reaches the peak of its 42-year-long seasons, this ice giant defies all expectations and erupts with a fury that rivals any planet in the solar system. The driving force behind this seasonal explosion is its extreme axial tilt. As each pole slowly swings into decades of continuous sunlight during its solstice, the atmosphere responds in a dramatic and delayed fashion. The hemisphere drenched in light begins to warm not from the weak sun but from the absorption of its meager energy, initiating a complex chain of atmospheric events. This triggers colossal convection currents, lifting methane gas from the deeper, warmer layers high into the upper atmosphere where it condenses into brilliant white clouds of methane ice. Voyager 2 saw a relatively calm world, but decades later, Earth-based telescopes and the Hubble Space Telescope witnessed a completely different Uranus during its equinox and solstice periods. They captured images of enormous cloud systems, some spanning thousands of miles, erupting across the planet's disk. These are not gentle wisps, they are powerful storm systems, evidence of an atmosphere crackling with dynamic energy. The most stunning displays are the bright polar caps that develop over the sunlit pole, a massive cap of reflective methane ice clouds that form under the relentless solar exposure. Beneath these cloud decks, winds howl at speeds that are almost incomprehensible, reaching velocities in excess of 560 miles per hour. To put that into perspective, that's more than twice the wind speed of the most powerful Category 5 hurricane ever recorded on Earth, screaming through an atmosphere that is negative 350 degrees Fahrenheit. The true mystery, however, is the engine driving this immense activity. With so little solar energy available and virtually no internal heat to stir the pot, what could possibly power such ferocious weather? Scientists are piecing together a fascinating answer that involves a form of planetary energy storage and release. They believe the key is Uranus's deep atmosphere, which acts like a massive thermal battery. During the long, dark winter, the atmosphere cools and contracts, effectively storing latent energy. When sunlight finally returns at the solstice, it doesn't just gently warm the surface, it penetrates deep and unlocks this stored energy, initiating a violent overturning of the atmospheric layers. This process releases pent-up energy in concentrated, powerful bursts, creating those giant storms and supersonic winds. It's a climate system governed by patience and extreme seasonal triggers, a world that spends decades building up energy only to unleash it in a breathtaking planet-wide storm season. This makes Uranus not a dormant giant, but a world of incredible climatic mood swings, its weather a direct and violent consequence of its unique and tilted place in the cosmos. Beyond the churning storms of its atmosphere lies a celestial court of silent witnesses, the 27 known moons of Uranus, each with its own story to tell. This isn't a unified family that formed together in a quiet disk of debris. It's a cosmic collection of captured strangers and shattered remnants, and their bizarre orbits present one of the most complex gravitational puzzles in our solar system. The moons are neatly divided into 3 distinct groups, and this classification is the first clue to their chaotic past. Closest to the planet are the 13 small, dark inner moons, which are likely remnants of a much larger moon that was shattered by a colossal impact. Their orbits are messy and intertwined, locked in complex gravitational dances that constantly jostle and perturb one another. Further out, we encounter the 5 major moons: Miranda, Ariel, Umbriel, Teutonia, and Oberon. These are the crown jewels of the Uranian system, complex worlds of rock and ice believed to have accreted from a disk of material surrounding the young planet. Most of them orbit in an orderly fashion, neatly aligned with the planet's extreme tilt and spinning in its equatorial plane, as if they formed from the same tipped-over disk. But it is the third group, the 9 irregular outer moons, that truly deepen the enigma. These are the rebels of the family, with their highly inclined, elliptical, and often retrograde orbits, meaning they circle Uranus in the opposite direction of the planet's own rotation. This is the telltale signature of captured objects. These moons, with names like Margaret, Francisco, and Ferdinand, did not form alongside Uranus. They are almost certainly ancient asteroids or Kuiper belt objects that strayed too close billions of years ago and were ensnared by the planet's gravity. Their existence itself isn't the mystery. Jupiter and Neptune also have families of captured irregular moons. The puzzle lies in their specific, and in some cases wildly unstable, orbital path. Take the moon Margaret, for instance. Its orbit is not only exceptionally eccentric, but is also currently changing in a measurable way. Gravitational perturbations from the Sun are slowly but relentlessly tugging at it, altering its path over millions of years in a complex interaction that models are still trying to perfectly replicate. Ferdinand, on the other hand, orbits in the opposite direction to most of the others, a trait that suggests it may have a completely different origin story from its irregular companions, perhaps captured at a different epoch in the solar system's violent early history. The very fact that these moons are still there at all is a question. Their unstable orbits mean they should have either crashed into Uranus, been flung out of the system, or collided with each other over the vastness of time. Their continued presence implies that our understanding of the gravitational dynamics at the edge of the Uranian sphere of influence is incomplete. Perhaps a series of delicate gravitational resonances between these moons helps to stabilize their paths, or maybe we are seeing them at a rare, quiet moment in a long cycle of orbital chaos. This collection of captured worlds points to a dramatic and violent youth for the seventh planet. To have so many large objects captured, Uranus must have formed in a much denser region of the primordial solar system, a crowded neighborhood where gravitational encounters with other protoplanets and planetesimals were frequent. The orbits of its outer moons are therefore frozen records of those ancient interactions, each one a clue to the dynamic processes that shaped the outer solar system and left Uranus with a gravitational family as unique and tilted as the planet itself. And yet, for all the chaotic orbital drama of its outer moons, the single greatest geological wonder in the Uranian system orbits much closer to the planet itself. If Uranus is the solar system's quiet eccentric, then its moon Miranda is its screaming enigma, a world that looks less like a natural celestial body and more like a cosmic jigsaw puzzle assembled by a madman. When Voyager 2 beamed back the first close-up images of this 300-mile-wide moon in 1986, scientists were utterly stunned. They were expecting a boring, cratered ball of ice, a fossil world frozen in time. Instead, they saw a geological nightmare, a scrambled landscape of bizarre, jagged features that defied all conventional explanation. Miranda's surface is a chaotic patchwork of wildly different terrains, juxtaposed with no apparent logic. Vast rolling plains covered in impact craters suddenly slam into enormous, grooved regions crisscrossed with parallel ridges and valleys, which then abruptly terminate at the base of sheer, monstrous cliffs that are among the tallest known in the entire solar system. The most jaw-dropping of these features are its 3 giant coronae, vast ovoid regions named Arden, Inverness, and Elsinore. These are not subtle markings, they are colossal geological tattoos etched across the moon's face. They resemble a complex racetrack pattern of concentric ridges and troughs, and they dominate the landscape. The cliff faces within and around these regions are of a scale that is almost impossible to comprehend. Verona Rupes, the most famous of these scarps, is a sheer cliff estimated to be 12 miles high. To put that vertiginous height into perspective, if you were to stand at its base and look up, the cliff face would soar over twice the height of Mount Everest, reaching from the surface well into what we would consider the edge of space. The forces required to thrust up and fracture ice to such an extreme degree are beyond anything we see on any other moon its size. So what incredible violence could have created such a world? The leading theories all point to catastrophic events in Miranda's deep past, and each one paints a dramatic picture. The first and most dramatic hypothesis is that of a colossal impact. It's possible that Miranda was once a much larger, differentiated moon, meaning it had separated into a dense core and a lighter mantle, and that it was struck by an object so immense that it literally shattered the moon to pieces. This impact would have been apocalyptic, vaporizing a huge portion of Miranda and scattering debris everywhere. What we see today, according to this theory, is the moon painfully reassembling itself from the fragments, gravity haphazardly pulling the chunks back together into a chaotic amalgamation of its former self. The coronae could be the scars of these immense collisions, or perhaps the sites where denser material from the deep interior welled up to the surface during the reassembly process, creating these unique pancake-like features. A second, more gradual theory points to the power of tidal heating. Early in the solar system's history, the orbits of Uranus's major moons may have been different, locked into gravitational resonances with one another. As they tugged on each other, their orbits would have become slightly elliptical, not perfect circles. This would have caused Miranda to flex and bend as it traveled around Uranus, its interior stretched and squeezed by the changing gravitational pull of the planet. This tidal friction generates an immense amount of internal heat, enough to partially melt its icy interior and drive tremendous geological activity. In this scenario, the coronae could be the frozen remains of massive icy plumes, similar to hotspots on Earth, where warm, slushy ice from the interior erupted onto the surface in colossal episodes of cryovolcanism, warping the landscape into those incredible ridges and troughs before the moon once again froze solid. A third idea suggests a process called incomplete differentiation. Perhaps Miranda was never fully homogeneous to begin with. It might have formed from a mixture of dense rock and lighter ice that never fully separated. As radioactive elements in the rocky material decayed, they would have generated heat, causing the denser rocks to slowly sink toward the center. But this process may have been messy and incomplete, with large chunks of rock remaining suspended in the ice. This uneven sinking and redistribution of mass could have created massive stresses in the moon's outer shell, triggering global tectonic cracking and thrusting up those unbelievable cliffs as the surface contorted to accommodate the shifting interior. Miranda stands as a stark reminder that even the smallest worlds can hold evidence of the most violent and transformative processes, a testament to the raw, creative power of destruction and rebirth in our solar system. While we've witnessed the bright, stormy explosions that accompany its long seasons, the atmosphere of Uranus holds another, far more elusive secret, one that lurks in the shadows rather than the light. For decades, astronomers suspected this distant world might host its own version of the great storms seen on Jupiter and Neptune. But it wasn't until the rise of powerful Earth-based observatories and the Hubble Space Telescope that they finally caught a fleeting glimpse. These are not brilliant white clouds of methane. They are vast, dark vortices, immense spinning storms that appear as deep, ominous spots against the planet's pale blue-green backdrop. The first definitive dark spot was imaged in 2006, a colossal feature nearly as wide as the continental United States, swirling in Uranus's northern hemisphere. Yet, unlike Jupiter's great red spot, which has been raging for at least 4 centuries, the dark spots of Uranus are here today gone tomorrow phenomena, appearing with little warning and vanishing again within just a few years or sometimes even mere months. The very nature of these spots makes them incredibly difficult to study. They are not permanent fixtures, they are atmospheric ghosts. Their transient behavior is the central mystery. Why do they form so suddenly, and what causes them to dissipate just as quickly? Scientists believe these dark vortices are massive high-pressure systems, anticyclonic storms where atmospheric gases are actually sinking rather than rising. As these gases plunge downward into the deeper, warmer layers of the atmosphere, they become compressed and heat up. This process is thought to cause any methane gas in the region to be pushed down below its condensation level, preventing it from forming the bright, reflective methane ice clouds that cover most of the planet. This leaves a clearing, a hole in the upper cloud deck, allowing us to see down into a darker, warmer, and deeper layer of the atmosphere that is normally hidden from view. What we perceive as a dark spot is essentially a window into the planet's abyss. But what triggers the formation of such a colossal sinking vortex in the first place, and why is its lifespan so brief? The answer likely lies in the peculiar and sluggish nature of Uranus's atmosphere. Without a strong internal heat source to drive constant, powerful convection, the atmosphere may develop pockets of instability that take a long time to build up. A slow, accumulating imbalance of temperatures and pressures deep within the atmosphere might eventually reach a tipping point, releasing its energy in a sudden, violent eruption that spawns one of these giant vortices. However, once formed, the storm might quickly starve. On a planet with robust internal heat like Jupiter or Neptune, storms are constantly being fed energy from below, allowing them to persist for centuries. On Uranus, that energy source is minuscule. The vortex forms, churns through its available energy, and then simply fades away as it's overcome by the surrounding atmospheric friction and wind shear, its structure dissolving back into the calm, cold haze. Their fleeting existence is a direct consequence of the planet's profound internal cold, making these dark spots not just fascinating weather patterns, but direct messengers from the frozen heart of the ice giant itself. While we've explored the visible and magnetic oddities of Uranus, some of its most intriguing signals are entirely invisible to our eyes, whispered in the language of energy itself. As Voyager 2 drew closer to the ice giant, its instruments picked up something both expected and utterly strange: radio waves. All magnetized planets with active atmospheres, like Jupiter and Saturn, produce powerful radio emissions, often generated by charged particles spiraling along magnetic field lines. These emissions usually pulse with a steady rhythm, tied directly to the planet's rotation, acting as a kind of celestial heartbeat that allows us to measure the length of its day even from billions of miles away. Uranus, however, broadcasts on a completely different frequency, both literally and figuratively. Its radio emissions are weak, highly unpredictable, and they flicker on and off in an intermittent, almost erratic pattern that defies easy explanation. This irregular cadence presents a significant challenge for scientists. On a planet like Jupiter, the source of these emissions is relatively straightforward. They originate from fixed regions near the magnetic poles, flashing like a lighthouse with every spin of the planet. But Uranus's magnetic field is a tumbling, off-center mess, and this profound asymmetry seems to be the key to the radio mystery. Because the magnetic field is so drastically tilted and offset from the planet's core, the conditions for generating strong, consistent radio bursts may only be met in very specific and fleeting circumstances. Imagine a lighthouse whose light only works when the storm waves hit it from one precise angle. During a calm sea or from any other direction, it remains dark and silent. Uranus's radio lighthouse is similarly capricious, only switching on when the turbulent solar wind. The constant stream of charged particles flowing from the sun strikes its wobbling magnetosphere at just the right orientation to trigger a burst of activity. The intermittent nature of these signals suggests that the underlying physical processes are far more complex than a simple, steady dynamo. One compelling theory points to magnetic reconnection, a process where the planet's tangled magnetic field lines break and rapidly realign with those carried by the solar wind. This reconnection acts like a slingshot, explosively accelerating electrons and generating sharp bursts of radio noise. On Uranus, the unusual geometry of its magnetosphere might make these reconnection events especially rare and unpredictable, occurring only during particular phases of its long orbit or during specific solar weather events. Another possibility is that the particles within its magnetic field are simply too sparse or too low energy to generate a strong, continuous signal. The same internal cold that leaves the atmosphere relatively calm might also mean there are fewer energetic particles zipping around to create the intense radio noise we detect from other giants. This radio puzzle is more than just a curious anomaly. It's a direct probe into the hidden workings of the planet's magnetic engine. By listening to these faint and sporadic whispers, scientists can infer details about the strength, density, and behavior of the charged particle populations trapped within Uranian space. Each burst is a tiny flash of insight, illuminating the complex dance between a wildly tilted magnetic field and the solar wind in a way that no other planet can. Decoding this irregular radio rhythm is crucial, as it may ultimately reveal the deepest secrets of the strange, superionic ocean swirling far beneath the clouds where the magnetic field is born. Adding another layer to the atmospheric puzzle, we come to a phenomenon that isn't a storm or a chemical, but a vast, ethereal shroud enveloping the entire planet, the strange and extended hydrogen corona of Uranus. When a planet has an atmosphere, the very outer fringes of that gaseous envelope can be heated and energized by solar radiation, causing the lightest atoms to achieve escape velocity and drift off into space. This creates a tenuous, glowing outer layer called a corona. Every giant planet has one, but when Voyager 2's instruments analyzed Uranus's, they found something completely unexpected. The hydrogen corona wasn't just present, it was enormous, reaching out to staggering distances from the planet, far more extensive and dense than any model had predicted for an ice giant. This discovery was a major surprise. Based on its distance from the Sun and its presumed internal temperature, scientists expected Uranus to have a relatively compact and modest corona, similar to what we might see around Saturn. Instead, they found a massive, puffy cloud of hydrogen atoms stretching out almost halfway to its moon Ariel. The immediate and pressing question was, how is this possible? What process is so efficient at hurling hydrogen atoms to such incredible altitudes against the pull of the planet's gravity? The leading theory points to a chemical process that acts like a giant planetary pump. It's believed that methane gas, which is abundant in the lower atmosphere, is being carried high up into the stratosphere by powerful seasonal circulation patterns. Once there, it's bombarded by ultraviolet radiation from the Sun. This radiation has enough energy to break the methane molecule apart, a process called photodissociation, which liberates its constituent hydrogen atoms. These atoms are incredibly light, and the energy from the solar radiation gives them a tremendous kick, sending them flying outward to form this immense extended corona. But this only deepens the mystery when we compare Uranus to its sibling, Neptune. The two planets are often called twins due to their similar size, mass, and composition. If this photodissociation process is driving the corona on Uranus, why doesn't Neptune have an equally massive one? This is the core of the anomaly. The answer may lie in the very thing that makes Uranus unique, its extreme axial tilt. That 98-degree roll fundamentally alters its atmospheric circulation and energy distribution in a way that Neptune, with its more conventional tilt, doesn't experience. During its solstice, one pole of Uranus is baked in continuous sunlight for 42 years. This persistent, focused heating likely drives much stronger and more efficient vertical mixing in the atmosphere, effectively acting as a conveyor belt that relentlessly transports methane-rich gases to the upper atmosphere where the Sun can break them apart. Neptune, with its more balanced seasons, might not have this same powerful pole-focused pumping mechanism, resulting in a weaker and more confined hydrogen corona. The implications of this vast hydrogen cloud are significant. A corona this extensive means that Uranus is likely losing its atmosphere at a much higher rate than previously thought. While the planet won't deflate anytime soon, it has an immense reservoir of gases. This ongoing loss is a key factor in understanding its long-term evolution and present-day composition. Furthermore, this extended shroud of hydrogen represents a physical barrier. For any future mission aiming to orbit the planet or conduct close atmospheric probes, engineers would have to account for the potential drag and interaction with this tenuous but far-reaching layer of gas. It's a reminder that even the most seemingly empty regions of space around a planet can be teeming with activity, a final whisper of an atmosphere slowly bleeding away into the infinite void. Yet the gravitational relationships within the Uranian system extend far beyond mere capture, weaving a complex and delicate web of influence among its inner moons. This brings us to one of the most intricate celestial ballets in the solar system, the puzzling orbital resonances that link Miranda, Ariel, and Umbriel. An orbital resonance is a beautiful and precise gravitational phenomenon where two or more orbiting bodies exert a regular, periodic influence on each other, often because their orbital periods, the time it takes to complete one lap around the planet, form a simple ratio of whole numbers. Think of it like two pendulums swinging at different speeds. Every few swings, they will line up at the same point, and the tiny pushes they give each other at that moment add up over time, creating a powerful, sustained interaction. For moons locked in resonance, these repeated gravitational nudges can provide a potent and continuous source of energy, profoundly affecting their geology and evolution. The current configuration suggests that these moons have not always occupied their present orbits. Billions of years ago, as the system evolved, they likely migrated outward from Uranus due to tidal interactions with the planet itself. As they moved, their orbital periods changed, and at certain critical distances, they inevitably fell into these gravitational syncopations. Data from Voyager 2 and subsequent modeling point toward a fascinating and complex chain of resonances that may have once included Miranda, Ariel, and Umbriel in a three-body dance. For instance, Ariel and Umbriel might have been locked in a 1-to-3 resonance, meaning for every one orbit Umbriel completed, Ariel would complete 3. Meanwhile, Miranda and Ariel could have been in a 1-to-2 resonance. These aren't just abstract numbers, they represent a clockwork mechanism of immense power. Every time the moons aligned at their orbital meeting points, they would give each other a gravitational tug, and over millennia, this constant pumping would have generated significant tidal friction within their interiors. This tidal heating is the key to unlocking the geological mystery of these moons, particularly the shocking surface of Miranda. The energy generated from being flexed and stretched in its resonant dance would have been more than enough to partially melt its icy interior, driving massive cryovolcanic eruptions and triggering the global tectonic upheaval that created its nightmarish landscape of coronae and cliffs. The same process likely affected Ariel, whose smooth plains and extensive network of valleys suggest a past era of resurfacing by icy lavas, and Umbriel, whose dark, cratered face hints at a history that was perhaps less violent or has been dormant for much longer. The most compelling evidence for this resonant past is the moon's present-day orbits. They are tantalizingly close to these perfect ratios but are not currently locked in them. This suggests we are seeing the aftermath of the dance, the echoes of a gravitational partnership that has since dissolved. The moons likely passed through these resonances during their outward migration, experiencing a relatively brief but incredibly intense period of geological activity before moving on and settling into their current, quieter orbits. The puzzle for scientists is reconstructing the exact steps of this ancient ballet and understanding why it ended. The dissolution of a resonance can happen if the outward migration proceeds too quickly or if the internal structure of a moon changes, altering how it responds to tidal forces. Miranda's bizarre composition, a possible result of a catastrophic impact and reassembly, could have changed its gravitational signature enough to throw the precise resonance off balance, causing the moons to fall out of sync. The orbital resonance puzzle is therefore a celestial detective story, where the present-day orbits and surfaces of these moons are the clues left behind from an era of dramatic gravitational forcing. It reveals a solar system that is not static and orderly, but dynamic and often chaotic, where worlds are not just shaped by their own internal processes, but by the relentless, rhythmic gravitational pull of their neighbors. Leaving the chaotic gravitational dances of the moons behind, we descend back into the atmosphere of Uranus itself, where we encounter a thermal phenomenon that defies the most basic laws of planetary behavior. As you rise through the troposphere of any typical planet, the temperature drops steadily the higher you go. But in the stratosphere of Uranus, this logic is completely inverted. Here, in a baffling meteorological twist, the atmosphere grows warmer with increasing altitude. This is the mysterious thermal inversion layer, an atmospheric anomaly where the rules of physics seem to have been flipped upside down, creating a warm blanket of gas suspended high above the deeper, colder layers below. So what strange mechanism is acting as a celestial space heater in this frigid environment? The prime suspect is a gas we've already met, methane. High in the Uranian stratosphere, methane doesn't just act as a cloud-forming compound, it transforms into a powerful solar energy sponge. The upper atmosphere is constantly bombarded by ultraviolet radiation from the sun. Methane molecules are exceptionally efficient at absorbing this high-energy light, converting the solar radiation into thermal energy plain and simple heat. This process directly warms the immediate surrounding gases, creating a defined layer of unexpectedly high temperatures. It's a similar principle to how the ozone layer heats Earth's own stratosphere, but on Uranus, methane is the primary driver, and the effect is far more pronounced due to the planet's unique seasonal extremes. However, the plot thickens considerably when we realize that methane absorption alone may not be sufficient to account for the full scale of the warming observed. This suggests that other, more exotic chemical processes are likely at work in this alien sky. One compelling theory points to a photochemical cascade initiated by that same solar UV radiation breaking apart methane molecules. The resulting hydrocarbon fragments, compounds like acetylene and ethane, can then go on to form a widespread, high-altitude haze. This haze itself is a brilliant absorber of solar radiation, and as these tiny particles drift downward through the stratosphere, they release the stored heat around them, further contributing to the overall warming of the layer and reinforcing the inversion. Another possibility involves the peculiar dynamics of Uranus's atmosphere. The weak internal heat and extreme seasons might create a situation where atmospheric circulation is unusually sluggish, trapping this absorbed heat in the stratosphere and preventing it from being efficiently mixed away, thereby intensifying the inversion effect. This thermal inversion is far more than a mere atmospheric curiosity. It acts as a potent cap, a lid on the planet's weather. By creating a stable layer of warm air over a colder one, it severely limits vertical mixing between the stratosphere and the troposphere below. This effectively stifles the kind of large-scale convection that drives the massive, continent-sized storm systems we see on a world like Jupiter. This could be a major reason why Uranus, for all its seasonal fury, often appears so deceptively calm and bland when viewed from a distance. The atmosphere's energy is trapped, its weather patterns confined and smoothed out by this invisible thermal blanket. Understanding this inversion is therefore critical to decoding the entire climatic system of the ice giant. It represents a delicate and complex balance between solar input, atmospheric chemistry, and internal dynamics. a balance that makes Uranus not just an oddball in its orbit, but in the very structure of its air. But this profound darkness only deepens the enigma, because when we examine the ring particles themselves, they present a composition that is unlike any other in our solar system. While Saturn's brilliant rings are composed of nearly pure water ice, reflecting sunlight with dazzling efficiency, the material making up the rings of Uranus is profoundly different. Spectroscopic analysis reveals that these particles are among the darkest materials we have ever observed, reflecting only a tiny fraction of the light that hits them. Their albedo, a measure of reflectivity, is lower than that of charcoal. This leads to the central question: what are these rings actually made of, and why are they so incredibly dark? Scientists are actively investigating several compelling theories to solve this puzzle of composition. The most straightforward explanation is a process known as radiation darkening. The rings of Uranus reside within the planet's powerful magnetosphere, a region filled with high-energy charged particles trapped by the magnetic field. Over billions of years, these particles have relentlessly bombarded the ring material. This constant radiation barrage is like a slow cosmic sandblaster, but its effect is chemical rather than physical. It breaks apart the molecules on the surface of the water ice, preferentially liberating the lighter hydrogen atoms and leaving behind a dense, complex crust of dark carbon compounds and other organic macromolecules. It's a process similar to how a plastic left in the sun becomes brittle and discolored, but on a planetary scale and over eons of time. The rings may have started with bright, icy surfaces, but they have been essentially baked into a dark, carbonaceous shell by this relentless radiation environment. However, an alternative theory suggests that the darkness might not be just a surface coating, but an intrinsic property of the ring material itself. Perhaps these rings did not form from a pure water ice object, but from a captured moon or planetary fragment that was already rich in dark, organic compounds. Objects from the outer solar system, like those found in the Kuiper belt, are known to be very dark due to a surface covering of complex organic compounds often referred to as tholins. These substances are created when simple ices like methane are irradiated, forming a reddish-brown or blackish tar like sludge. If the rings are the remnants of a captured Kuiper belt object or a dark, carbon-rich moon that was torn apart by Uranus's gravity, then they would have been born dark. Their composition would be a direct fossil record of their origin, telling a story of a violent capture and disintegration in the distant past, rather than a gradual process of surface weathering. This mystery of composition is not merely an academic exercise. It holds the key to understanding the entire history and evolution of the Uranian system. The nature of the ring material acts as a time capsule, preserving clues about the environment in which it formed and has existed. If radiation darkening is the primary cause, it tells us about the intensity and history of the planet's magnetospheric environment. If the rings are inherently dark, it points to a specific and dramatic origin story involving the capture of a primitive body from the cold outer reaches of the solar system. Unlocking this secret would provide a critical piece in the puzzle of how not only the rings, but the entire family of moons and the planet itself came to be the strange and unique system we observe today. Moving from the strange thermal layers of the stratosphere, we plunge into the chaotic heart of the Uranian atmosphere itself, where winds defy all convention and logic. Here, the very air is engaged in a planetary scale war of currents, a phenomenon of extreme wind shear that stands as one of the most perplexing meteorological puzzles in our solar system. On most planets, wind patterns follow a somewhat predictable pattern, often aligned with the planet's rotation, but Uranus is a world of atmospheric rebellion. At its equator, the winds blow in a retrograde direction, meaning they move opposite to the planet's own spin. Yet, as you journey toward the mid-latitudes, these winds gradually slow, come to a complete stop, and then reverse course entirely, screaming in a prograde direction at higher latitudes. This creates a breathtakingly complex pattern of opposing jet streams and violent shear zones, a turbulent tapestry of moving air that has no direct parallel on any other world. The sheer speed of these winds adds to the awe. While the equatorial retrograde winds are relatively sluggish, the prograde winds at latitudes around 60 degrees are another story entirely. They can accelerate to a phenomenal 560 miles per hour, faster than any wind recorded on Earth and rivaling the most powerful jets on Neptune. This creates unimaginable turbulence at the boundaries between these opposing currents, where a traveler would experience a catastrophic change in wind speed and direction over a relatively short horizontal distance. The energy required to sustain such a chaotic and powerful system of opposing flows is immense, and on a world with so little internal heat to drive weather, its very existence is a profound mystery. Unraveling the engine behind this atmospheric contradiction forces scientists to look at the unique combination of factors that make Uranus so strange. The leading theory points directly to the planet's extreme seasons and its lack of internal heat. Unlike Jupiter or Saturn, which have powerful internal engines driving their weather from the bottom up, Uranus's atmosphere is primarily driven from the top down by the feeble but focused input of solar energy. During its long solstice, one pole is drenched in continuous sunlight for decades. This likely sets up massive, planet-wide circulation cells as the atmosphere attempts to redistribute this uneven heating from the hot pole to the cold pole. The Coriolis effect, caused by the planet's rotation, then twists these giant overturning circulations into the complex east-west wind patterns we observe. The retrograde equatorial winds might be a kind of atmospheric backlash, a return flow that completes the circulation cells set in motion by the intense heating at the summer pole. Another compelling idea involves the interaction between the deep atmosphere and the overlying layers. The same sluggish atmospheric mixing that creates the thermal inversion may also play a role in segregating these wind zones. If there are few processes to mix momentum between different atmospheric layers, the winds at various depths and latitudes could become effectively decoupled, allowing them to develop and maintain their own independent directions and speeds. The bizarre, off-center magnetic field might even contribute, as its interactions with the solar wind could indirectly deposit energy into the upper atmosphere in uneven ways, further stirring the pot of this already volatile meteorological system. The extreme wind shear of Uranus is therefore not a single mystery but the visible outcome of a perfect storm of oddities. A tipped-over planet, a frozen core, and a climate driven by sunlight alone, all combining to create an atmospheric dynamo of breathtaking complexity and power. But if you thought the Uranian magnetic field couldn't get any stranger, prepare for a possibility that pushes the boundaries of planetary physics into the realm of the truly surreal. The chaotic, tumbling nature of its magnetosphere has led some scientists to propose a truly radical idea: that Uranus's magnetic field may not be stable at all, but could instead be prone to spontaneous and frequent reversals. On Earth, a full magnetic polarity flip is a rare cataclysm that occurs over thousands of years, but for Uranus, this process might be a regular and chaotic event, happening on a scale of decades or even less, transforming its protective magnetic bubble into a temporary and unreliable shield. The evidence for this wild possibility is rooted in the field's profound instability, because it's generated in a relatively thin, slushy shell of supersonic water and ammonia, rather than a deep, stable core of molten iron. The Uranian magnetic dynamo is fundamentally different from Earth's. It's a messy, turbulent process, highly sensitive to the complex convective flows and temperature differences within that exotic ocean. Computer simulations suggest that such a shallow, fluid-driven dynamo could be inherently chaotic, prone to sudden flips and even periods where the field isn't a simple two-pole bar magnet at all, but a complex multipolar mess, a tangled web of multiple north and south poles popping in and out of existence across the planet's surface. Voyager 2's brief snapshot in 1986 showed a field that was already drastically tilted and offset. It's entirely plausible that this was merely one frame in a much longer, more erratic film of magnetic activity. The consequences of such a volatile magnetic personality would be profound, especially for the structure of the magnetosphere and the planet's protection from the solar wind. During a stable period, even a tilted field provides a substantial buffer, deflecting charged particles and creating a recognizable magnetosphere. But during a reversal or a multipolar breakdown, that protection could utterly collapse. The field lines could become so tangled and disorganized that they effectively open giant gaps, allowing the full fury of the solar wind to pour directly into the upper atmosphere, stripping away gases and triggering massive auroral storms across the entire planet. This could explain the planet's extensive hydrogen corona. If the magnetic shield frequently fails, the atmosphere would be far more vulnerable to erosion over billions of years. Furthermore, the radiation environment for any potential moons would become a nightmare, with charged particle fluxes wildly fluctuating between calm and lethal, potentially sterilizing their surfaces in regular, violent bursts. The idea of a spontaneously reversing magnetic field turns Uranus from a merely peculiar world into a fundamentally unpredictable one, a planet where the very rules of physics seem to be rewritten on a cosmic whim. Deep within the layered atmosphere of Uranus, at a specific and precise altitude, a beautiful and perplexing meteorological phenomenon takes shape: brilliant white clouds of methane ice. Unlike the vast, continuous cloud decks that band Jupiter and Saturn, the methane clouds on Uranus appear as discrete, isolated layers, forming and dissipating in specific, narrow zones like delicate sheets of lace suspended in the pale blue sky. This highly stratified cloud structure is a signature feature of the Uranian atmosphere, and its formation is a direct and fascinating consequence of the planet's profound internal cold and unique atmospheric chemistry. To understand why these clouds form in such a distinct way, we must take a journey down through the alien air of this ice giant. The process begins with the basic ingredients. The atmosphere of Uranus is primarily hydrogen and helium, but it is laced with a small but crucial amount of methane, about 2.3%. While this seems minor, it is more than enough to drive cloud formation under the right conditions. As we descend from the cold, upper reaches of the atmosphere, both the temperature and the pressure begin to rise dramatically. At a very specific depth, where the temperature hovers around -330 degrees Fahrenheit and the pressure is about 1.2 bars, just slightly greater than Earth's surface pressure, we hit the sweet spot. This is the methane condensation level, the exact point where the ambient conditions cause methane gas to transition directly into solid ice crystals. It's a process akin to water vapor in Earth's atmosphere freezing into cirrus clouds, but occurring in an environment of unimaginable cold and with a completely different chemical. So why does this create such a thin, discrete layer instead of a thick, fluffy deck? The answer lies in the extreme stability of Uranus's atmosphere, a direct result of its missing internal heat. On a world like Jupiter, powerful convection currents, great plumes of warm gas rising from the hot interior, constantly churn the atmosphere. This turbulence carries cloud-forming materials like ammonia and water vapor high up through multiple layers, creating thick, mixed cloud decks that can span dozens of miles in altitude. Uranus lacks this powerful internal engine. Without strong convection to stir the pot, its atmosphere is far more stratified and sluggish. Materials don't get vigorously mixed across different levels, they tend to stay put. This means that methane gas is largely confined to its own specific layer in the atmosphere. When conditions are right for it to condense, it can only do so in that one narrow band, creating a wafer-thin sheet of ice crystals that is sharply bounded above and below by clear air. The formation of these clouds is also intimately tied to the planet's extreme seasons. During the decades-long summer solstice, when one pole is continuously baked in sunlight, atmospheric circulation patterns act like a giant conveyor belt. They draw methane-rich gases from the deeper, warmer layers upward toward the cold, sunlit pole. When this gas reaches the precise altitude of the methane condensation level, it instantly freezes, creating a brilliant, bright polar cap of concentrated methane ice clouds, a seasonal crown that observers on Earth can actually see with powerful telescopes. As the season changes and the pole moves into darkness, this conveyor belt slows and eventually reverses, causing the spectacular cloud cap to slowly fade away until the next solstice. This seasonal control adds another layer of complexity, making the methane clouds not a permanent feature, but a dynamic and transient display driven by the slow, relentless turning of the Uranian year. While its internal composition and chaotic weather present compelling puzzles, the very position of Uranus in our solar system holds a mystery that reaches back to the very beginning. The orderly spacing of the planets, often depicted in simple diagrams, is now understood by scientists to be a snapshot of a far more dynamic and violent history. For Uranus, this raises a profound question. Has it always orbited the Sun at this distant, frigid address, or did it undergo a dramatic journey in the solar system's tumultuous youth? This is the mystery of planetary migration, and the clues pointing to Uranus's potential wanderlust are written in the architecture of our entire cosmic neighborhood. The leading model for how our solar system formed, the NICE model, suggests that the giant planets did not form in their current locations. Instead, they emerged from the primordial disk of gas and dust much closer together in a far more compact configuration. According to this theory, a gravitational dance of instability between Jupiter and Saturn eventually triggered a massive rearrangement that sent Uranus and Neptune scattering outward into the colder, sparser regions of the outer solar system. This grand tack, as it's called, would have been a period of incredible chaos, with these ice giants plowing through a dense sea of leftover planetary building blocks, scattering some into the distant Kuiper belt and hurling others inward in a theorized event called the Late Heavy Bombardment that pelted the inner planets. The very fact that Neptune is now the outermost planet, despite being more massive than Uranus, is a strong piece of circumstantial evidence for this migration. It's far easier to explain this inverted order if both planets moved outward, with Neptune being flung just a bit farther than its sibling due to its specific gravitational interactions. The composition of Uranus itself provides another tantalizing chemical clue. As we discussed earlier, its atmosphere is rich in hydrogen sulfide, the compound that gives rotten eggs their smell, and is strikingly deficient in ammonia compared to expectations. This specific chemical fingerprint suggests it formed in a region of the protoplanetary disk that was even colder and more remote than its present position. The compounds that condense into ice grains, the fundamental building blocks of planets, vary dramatically with temperature. Water ice condenses relatively close to the Sun, followed by ammonia ice further out, and finally methane and other hydrogen sulfide ices in the coldest, most distant reaches. The prevalence of hydrogen sulfide ice in its composition implies that Uranus accreted from materials that could only have existed in a much frostier environment, far beyond its current orbit. It's as if we found a person who grew up in the Arctic now living in a temperate forest, still wearing their heavy parka and surrounded by clues to their true origin. Perhaps the most compelling evidence for this migration, however, comes not from Uranus itself, but from the trove of captured objects in its gravitational sphere. The irregular outer moons with their wildly inclined and retrograde orbits are the planet's permanent record of its travels. To have captured so many sizable objects, Uranus must have moved through a region that was once extremely densely populated with primordial planetesimals, the small, icy bodies left over from the solar system's formation. A planet forming in situ in its current quiet orbit would have a much smaller and less diverse collection of captured moons. The vast and chaotic family of irregulars orbiting Uranus is a clear signpost of a violent past, a gravitational haul collected as the planet plowed through the crowded outer disk. Each of these captured moons is a souvenir from a different part of its migratory path, a silent testament to a journey of billions of miles that fundamentally shaped the solar system we see today. This profound delay in its seasonal response presents yet another atmospheric conundrum, one that speaks to the immense depth and complexity hidden beneath those serene blue clouds. On any typical planet, you would expect the warmest temperatures to coincide with the summer solstice, the point of maximum solar exposure. For Uranus, this logic is completely upended. Even after its pole has been baking in continuous sunlight for years, the atmosphere remains stubbornly cold. The peak temperatures don't arrive until years, sometimes even decades, after the solstice has passed. It's as if the entire world is operating on a colossal time delay, its climate responding to the seasons with a sluggishness we see nowhere else. This seasonal lag is a direct signal that Uranus's atmosphere is not a thin, responsive skin, but a deep, massive, and incredibly slow-moving ocean of gas. Unraveling the cause of this lag forces us to consider the sheer scale of the Uranian atmosphere and its profound lack of internal energy. The leading theory points to the planet's incredible thermal inertia. Think of a massive pot of water on a stove. A small flame will take a very long time to bring it to a boil because the water has to absorb a tremendous amount of energy before its temperature significantly changes. Uranus's atmosphere is that pot, but on a planetary scale. It is overwhelmingly deep and massive, composed primarily of hydrogen and helium, which have a very high heat capacity, meaning they require a vast amount of energy to warm up even a little. The feeble trickle of energy from the distant sun is simply not enough to quickly heat this immense reservoir of gas. The atmosphere must slowly, gradually absorb solar energy over many years before it finally begins to show a measurable temperature response. Furthermore, the missing internal heat exacerbates this effect dramatically. On Earth and even on Neptune, internal heat acts as a constant baseline source of energy, helping to drive atmospheric circulation and mix heat more efficiently. Uranus has no such engine. Without this internal stirring, the atmosphere becomes incredibly stratified and sluggish. The process of transporting heat from the sunlit pole down into the deeper layers and across to the dark hemisphere is not driven by powerful convection but by much slower, large-scale circulation patterns. This is likely a languid, planet-wide overturning circulation, a kind of gargantuan conveyor belt that moves at a glacial pace. It takes an immense amount of time for the heat absorbed at the top of the atmosphere to be mixed downward and distributed across the globe, creating this multi-decade lag between cause and effect. This seasonal lag is far more than a curious observation. It is a critical key to modeling the ice giant's complex climate system. It provides scientists with a way to indirectly measure the efficiency of heat transport within the atmosphere's deepest layers, regions we cannot directly observe. The length of the delay tells us about the atmospheric density, the mixing rates, and the overall energy budget of the planet. It paints a picture of a world that is not just cold but thermally ponderous, its climate system moving with the slow, deliberate rhythm of a celestial giant, forever playing catch-up with the seasons. This striking variation in surface appearance across the 5 major moons presents a geological timeline frozen in time, a record of internal fire and external violence that tells a unique story for each world. We see everything from Miranda's horrifically fractured visage to the dark, ancient, and seemingly unchanged face of Umbriel. This moon surface dichotomy is a direct window into the vastly different levels of internal activity and thermal history each of these worlds has experienced, forcing us to ask why such similar-sized bodies, formed in the same region around the same planet, could have ended up so completely different. Let's start with the two extremes. On one end of the spectrum, we have Miranda, a world that looks as if it was shattered and haphazardly glued back together. Its Coroni, canyons, and 12-mile-high cliffs scream of a past filled with immense, concentrated energy. Next to it, Umbriel represents the absolute opposite. It is the darkest of the major moons, with a surface that is uniformly ancient and heavily cratered, showing no obvious signs of any large-scale resurfacing events in billions of years. It appears to be a fossil, a primordial world that has been geologically dead for almost the entire history of the solar system. Then we have the middle ground, Ariel and Titania. Both show extensive evidence of past geological activity. Ariel boasts the most extensive network of fault valleys and smooth plains, suggesting a significant period of tectonic stretching and possible cryovolcanic resurfacing. Titania, the largest moon, has gigantic rift valleys and some smoother regions, indicating it too had enough internal heat to break its surface in the distant past. Oberon, the outermost major moon, seems to be a slightly more active version of Umbriel, with its old, cratered surface punctuated by a few hints of internal activity, like mysterious dark material that may have erupted from its interior onto the floors of some craters. So why did Miranda experience such apocalyptic violence while Umbriel slept peacefully? The answer almost certainly lies in the powerful but temporary effects of orbital resonance. As we discussed earlier, the gravitational dance between Ariel, Umbriel, and Miranda billions of years ago would have pumped tidal energy into their interiors, flexing them and generating significant heat. However, this heating would not have been uniform. Miranda, being the smallest and least massive, would have been the most vulnerable to this tidal forcing. The same amount of energy that would gently warm the interior of a larger moon like Titania could have been enough to partially melt Miranda's interior entirely, triggering the catastrophic resurfacing that created its nightmare landscape. Ariel, being next in size, also received a substantial dose of this tidal heat, explaining its extensive valleys and smooth plains. The resonance would have had a much weaker effect on the larger, more massive moons like Titania, Umbriel, and Oberon. Their greater size acted as insulation, preventing the tidal energy from triggering widespread surface changes, leaving them largely frozen in time. But this doesn't fully explain Umbriel's profound darkness and complete lack of activity compared to its similar-sized sibling Titania. This is where composition and internal structure likely come into play. Umbriel may simply be a different kind of world beneath its surface. It might have a lower concentration of radioactive elements in its rocky core, providing less long-term heating from rock decay. Its internal composition might also include more antifreeze compounds like ammonia, which would lower the melting point of its ices and allow it to stay solid and rigid under conditions where other moons would begin to soften and flow. It's possible Umbriel formed further out in the Uranian subnebula where darker, carbon-rich materials were more abundant, giving it a crust that was inherently less reflective from the very beginning. Titania, by contrast, may have formed with a hotter, more radioactive core and a purer ice shell, allowing it to maintain a more geologically active personality for a longer period. The surface dichotomy of these moons is therefore a story written in ice and rock, a tale of size, location, and gravitational fortune. Miranda, the smallest, was the victim of intense tidal trauma. Ariel, sitting in the sweet spot, experienced enough energy to renew its surface without being torn apart. The larger moons, Titania and Oberon, experienced only brief, muted geological awakenings. And Umbriel, whether by composition or cosmic luck, slept through it all, preserving a face from the solar system's earliest days. Together, they form a complete geological family portrait, each member telling a different part of the story of how forces from within and without shape the worlds of the outer solar system. And yet, even the planet's most dazzling light shows are tinged with profound mystery. Here on Earth, the aurora borealis and aurora australis are magnificent, predictable curtains of light that dance in neat ovals around our magnetic poles. On Uranus, the rules of this celestial ballet are completely rewritten. The auroras here are faint, erratic, and bizarrely misplaced ghostly illuminations that flicker to life in unexpected locations, refusing to conform to the elegant patterns we see on every other magnetized world. They are not concentrated in tidy rings around the magnetic poles. Instead, they appear as scattered, patchy glows that can emerge far from where any model predicts they should be, adding another layer of enigma to this already perplexing ice giant. The root of this auroral anomaly lies in the very thing that makes Uranus so unique: its chaotically tilted and offset magnetic field. On a planet with a standard dipole magnet aligned with its rotation axis, like Earth or Jupiter, the process is relatively straightforward. The solar wind, a stream of charged particles from the Sun, is funneled by the magnetic field lines down into the upper atmosphere near the poles. There, these particles collide with atmospheric gases, exciting them and causing them to release energy in the form of light. The entire phenomenon is neatly organized by the planet's magnetic geometry, but Uranus's magnetic field is a tumbling, lopsided mess. Its magnetic poles are located nowhere near its geographic poles, and the entire field is tilted at a staggering 59-degree angle. This means the regions where charged particles are funneled into the atmosphere are constantly shifting and wobbling as the planet rotates, creating a moving target for auroral formation that is incredibly difficult to predict or even observe. This bizarre magnetic geometry forces the auroral activity into a state of permanent irregularity. Because the magnetic field is so asymmetric, the solar wind does not interact with it in a consistent way. The strength and orientation of the solar wind pressure can cause the Uranian magnetosphere to reconfigure itself on the fly, opening and closing different magnetic pathways to the atmosphere. An aurora might suddenly ignite on the day side of the planet when a burst of solar wind compresses the magnetic field, only to vanish just as quickly when conditions change. Furthermore, the extreme seasons play a crucial role. For 42 years, one magnetic pole is pointed almost directly at the Sun, while the other is in total darkness. This results in a dramatic imbalance in how solar energy is delivered to the magnetic environment, potentially leading to auroras that are vastly different in brightness and structure between the two hemispheres depending on the time of the Uranian year. The faintness of the displays is another puzzle, likely tied to the planet's lack of internal heat and a potentially sparse population of energetic particles within its magnetosphere available to create a brilliant show. Detecting these elusive lights has been a monumental challenge for astronomers. The first confirmed observations didn't come until 2011, when the Hubble Space Telescope trained its powerful eye on Uranus and managed to capture fleeting glimpses of these faint ultraviolet glows. Later, scientists re-examined decades-old data from the Voyager 2 flyby and found evidence of auroral activity there as well, hidden in the readings all along. Each observation only deepens the mystery, revealing auroras that are not only faint and patchy, but also seem to be generated by different processes than those on other planets. Some may be driven by the solar wind, while others could be powered by internal mechanisms within Uranus's own magnetosphere, such as those chaotic magnetic reconnection events. These ghostly lights are therefore much more than a beautiful sideshow. They are a direct visual manifestation of the planet's broken magnetic heart, a flickering cipher that scientists must decode to truly understand the complex and hidden forces at work within this distant, tilted world. Yet high above the turbulent weather and methane cloud decks lies an atmospheric feature of surprising delicacy and structure. the multiple, distinct layers of haze that envelop Uranus in a series of pale, blue-green veils. Unlike the chaotic and transient dark spots or the supersonic winds, these haze layers are a permanent and finely tuned feature of the upper atmosphere, forming at incredibly specific altitudes with a precision that seems almost manufactured. This isn't a homogeneous smog, it's a stratified onion skin of aerosols, each layer holding clues to the complex chemical orchestra playing out in the sunlight above the clouds. The existence of such well-defined layers on a planet with such feeble energy sources is a puzzle in itself, pointing to a delicate balance of processes that we are only beginning to understand. The journey to create these hazes begins with a relentless downpour of solar energy. High in the stratosphere, ultraviolet radiation from the sun relentlessly bombards methane molecules. This intense light has enough energy to break the chemical bonds holding methane together, a process known as photodissociation. This shatters the methane, liberating its hydrogen atoms and leaving behind reactive hydrocarbon fragments. These fragments are the building blocks of the haze. Molecules like acetylene and ethane quickly form from this chemical carnage, and they begin to slowly polymerize, linking together into ever larger and more complex chains of carbon and hydrogen. Eventually, these chains grow heavy enough to condense out of the gas, forming countless tiny, solid particles that are suspended in the upper air, creating the haze we observe. It's a slow, top-down manufacturing process, a cosmic factory that uses sunlight as its power source and methane as its raw material. But why do these particles arrange themselves into discrete, separate layers instead of a single, uniform fog? The answer lies in the intricate vertical circulation patterns of Uranus's atmosphere, which act like a series of invisible conveyor belts. While the atmosphere lacks the violent convection of Jupiter, it is not completely still. Scientists believe there are very slow, large-scale overturning circulation cells at work. These cells gently lift gases from the warmer, deeper layers over the course of years, carrying them up to specific altitudes in the stratosphere. At these precise levels, the combination of temperature and pressure creates a kind of trapping zone, a region where the newly formed haze particles can accumulate and persist, held in a delicate equilibrium between the weak upward drafts and the gentle pull of gravity trying to drag them back down. Each distinct haze layer likely represents a different branch of this sluggish atmospheric circulation, a separate conveyor belt delivering its chemical payload to a predefined altitude. The composition of these haze particles adds another layer to the mystery. Data from Hubble and ground-based telescopes suggest they are not simple hydrocarbons, they are likely rich in tholins. Tholins are complex, macromolecular organic compounds that form when simple hydrocarbons like methane are irradiated over long periods. They are not a specific compound but a class of reddish-brownish, tar-like substances that are thought to be common on cold bodies in the outer solar system, giving places like Pluto its reddish hue and coloring the dark sides of Uranus's moon. On Uranus, these tholin particles would be excellent at absorbing blue light, which helps explain the planet's distinctive and uniform aquamarine color. The haze layers act as a planet-wide filter, scattering sunlight and bathing the entire world in that serene, blue-green glow that makes it so visually unique among the giants. The persistence and stability of these haze layers, despite the planet's extreme seasons, is their final compelling puzzle. As Uranus journeys through its 84-year orbit, the amount of solar energy each hemisphere receives changes dramatically. Yet the haze layers remain a constant shroud. This suggests that the photochemical processes that create them and the atmospheric circulation that shapes them are remarkably robust and self-regulating. The slow, ponderous nature of the Uranian climate may work in the haze favor. The timescales involved are so long that these layers represent a long-term average of atmospheric activity, immune to short-term fluctuations. They are a permanent, etched record of the complex and slow-motion interplay between the faint sun above and the frozen, silent world below, a delicate and beautiful signature of chemistry played out on a planetary scale. But the very existence of these dark, narrow bands of debris leads us to one of the most fundamental and unresolved debates in planetary science. Just how old are they? This is the Ring Age controversy, a puzzle that forces us to question whether we are looking at a primordial feature, an ancient relic from the very birth of Uranus itself, or a far more recent and dramatic addition to the system, the scattered remains of a moon torn apart in a catastrophic collision. The answer to this question isn't just about dating some icy rubble. It's a key that unlocks a completely different history for the entire Uranian system. On one side of the debate, the primordial theory argues that the rings are almost as old as the planet. According to this view, they are leftover material from the protoplanetary disk that formed Uranus, a belt of debris that never managed to coalesce into a full-sized moon. This could have happened if the material orbited within the planet's Roche limit, the gravitational boundary where the tidal forces from Uranus are so strong that they prevent any loose particles from ever accreting into a larger body. In this scenario, the rings have been continuously shaped and confined by shepherd moons for over 4.5 billion years, a stunningly ancient and delicate feature that has somehow survived the violent chaos of the early solar system. The primary evidence for this great age lies in their very darkness. If the rings were primordial, they would have been subjected to billions of years of relentless radiation bombardment from the solar wind and charged particles within Uranus's magnetosphere. This would have thoroughly darkened any initially bright ice, creating the deep, carbon-rich crust we observe today. Their current state seems to be a perfect match for this slow, gradual process of radiation darkening acting over an immense span of time. The opposing view, the recent origin theory, paints a far more dramatic picture. It proposes that the rings are a transient and fleeting phenomenon on a cosmic timescale, perhaps only a few 100 million years old. In this scenario, the rings are the expanding debris field from a massive collision that occurred relatively recently in the solar system's history. The catastrophic destruction of a mid-sized moon, or perhaps a violent encounter between two of Uranus's existing satellites. This event would have blasted an enormous amount of fresh, bright ice and rock into orbit around the planet. The darkness of the rings from this perspective is not a sign of great age but of rapid contamination. The debris would have quickly become coated in dark material from the impact itself, carbon-rich compounds from the shattered moon's interior, and then rapidly darkened further by the intense radiation environment. This theory finds support in the ring's remarkable narrowness and sharp edges. Such precise structures are dynamically young features. Over hundreds of millions of years, the natural processes of collisions and gravitational interactions between ring particles should have caused them to spread out and become more diffused. Their current well-defined nature suggests they have not had enough time to dissipate, pointing to a more recent origin. Furthermore, the complex gravitational resonances that might help maintain them could be a temporary phenomenon, a snapshot of a system that is still settling down after a recent violent upheaval. The truth may lie somewhere in the middle, or perhaps involve a more complex hybrid history. It's possible that a primordial ring system did exist but was faint and tenuous, only to be dramatically replenished and reshaped by a more recent breakup of a moon, creating the dense, narrow rings we see today. Data from future missions will be crucial to settling the debate. Precise measurements of the ring particle size distribution could provide clues. A wider spread of particle sizes might indicate an older ring that has undergone more collisional evolution, while a narrower range could point to a younger, fresher debris field. A detailed analysis of the exact chemical composition of the dark material could also be a telltale sign, revealing whether it was created by eons of radiation or in the instant of a single shattering impact. The age of the rings of Uranus is therefore not a mere academic footnote. It is the story of the planet's past written in ice and dust, Are they ancient scribes whispering secrets from the dawn of the solar system, or are they the vibrant, short-lived offspring of a more recent cosmic catastrophe? For now, they keep their secret, a timeless enigma circling a timeless world. This final mystery brings us to the very core of the ice giant paradox. When we place Uranus and Neptune side by side, we encounter a fundamental contradiction that challenges our most basic models of how planets are built. Here are the simple, undisputed facts. Neptune is more massive than Uranus, yet somehow Uranus is denser. This is the density paradox, and it turns planetary formation theory completely on its head. In the simplest terms, if you could place both planets in a cosmic ocean, the larger, more massive Neptune would actually float, while the smaller Uranus would sink. This defies all logic, as we would naturally expect the more massive object to have stronger gravity, and thus to compress its interior more, resulting in a higher density. The fact that the reverse is true suggests that the two planets, long considered twins, are in fact built from entirely different blueprints. To resolve this puzzle, scientists must look past the total mass and into the specific ingredients and internal structure of each world. The leading hypothesis points to the planet's rocky cores. It's possible that Uranus simply has a larger proportion of heavy rock and metal elements compared to ices like water, methane, and ammonia. Imagine making two cakes of different sizes. The smaller cake could still be denser if it was made with a much higher ratio of flour to light, fluffy frosting. In this scenario, Uranus formed from building blocks that were inherently denser, perhaps because it accreted material from a region of the protoplanetary disk that was richer in silicates and metals, while Neptune's formation zone was dominated by lighter ices. A second, and perhaps more compelling, theory involves the colossal impact thought to have tipped Uranus on its side. This catastrophic event may have done more than just reorient the planet. It could have fundamentally scrambled its interior. The unimaginable energy of the impact might have blasted away a significant portion of the planet's original, light atmosphere of hydrogen and helium, leaving behind a disproportionately large core of heavy elements relative to its gaseous envelope. Neptune, having avoided such a violent trauma, would have retained more of its primordial light gases, making it larger in size but less dense overall. This would mean that Neptune represents the standard model for an ice giant, while Uranus is the outlier, its density a permanent scar from an ancient cosmic collision. A third possibility delves into the subtle differences in internal structure and composition that could affect how much each planet has compressed over billions of years. Even a small variation in the abundance of a single element could have a cascading effect. For instance, if Neptune has a higher concentration of methane in its mantle, the breakdown of this compound under extreme pressure could generate carbon diamonds that rain down into the core. This process would effectively separate lighter elements from heavier ones, concentrating mass in the planet's center and increasing its overall density. If this diamond rain is more prolific on Neptune, it could be the key to its unexpectedly lower density compared to its sibling. Ultimately, the density paradox forces us to accept that Uranus and Neptune are not identical twins, but fraternal ones, products of different formation histories, different childhood environments, and different traumatic events that have left them with unique and deeply personal internal identities. Deep within the crushing pressures and unimaginable cold of Uranus's atmosphere, a theoretical spectacle unfolds that challenges our very understanding of matter itself. We descend past the methane ice clouds and the hydrogen sulfide haze, journeying into a realm where pressure mounts to millions of times that of Earth's surface and temperatures soar to thousands of degrees, not from heat but from compression. Here, in this alien interior, the common elements of life are transformed into something extraordinary. Methane, a simple molecule of one carbon atom bonded to 4 hydrogen atoms, cannot survive such extremes. The incredible pressure literally squeezes the hydrogen atoms away, liberating the carbon atoms and forcing them to link together in tight, crystalline lattices. This is the birthplace of a phenomenon found nowhere else in our solar system, a steady, glittering rain of solid diamonds. The process is both elegant and violent. It begins with a vast ocean of supersonic water and ammonia that makes up the planet's mantle. This slushy, electrically conductive fluid is believed to be rich in dissolved methane and other hydrocarbons that have settled from the upper atmosphere. As this material sinks deeper into the planet, the environment becomes more and more hostile. The pressure intensifies to a point where the bonds holding the methane molecules together simply snap. The freed carbon atoms, under this relentless squeezing, are compelled to form the highly stable structure of diamond. These newly formed diamonds, far heavier than the surrounding slushy ocean of water, ammonia, and hydrogen, immediately begin to sink. They fall like hard, glittering hailstones through thousands of miles of strange fluid, gathering in size as they descend, potentially accumulating into a thick layer of diamond-rich sediment around the planet's rocky core. Some models even suggest there could be literal diamond icebergs floating in the metallic ocean or vast subterranean mountain ranges of crystalline carbon. But the exotic precipitation may not stop at diamonds. The same extreme conditions that forge carbon into gems could be creating other, even stranger forms of matter. As the diamonds plummet through the hydrogen-rich environment, some scientists theorize a further transformation could occur. The immense pressure at the very deepest layers might be enough to compress the diamonds themselves into a liquid metallic form, creating a rain not of stones but of liquid carbon. Imagine not glittering gems but a shower of conductive metallic fluid, a form of matter that blurs the line between a mineral and a metal. Furthermore, the liberated hydrogen, no longer bound to carbon, would form its own precipitation. In the upper layers of this deep atmosphere, it might condense into a rain of liquid helium droplets, a superfluid that defies the normal laws of friction and viscosity. The interior of Uranus, therefore, may not be a homogeneous fluid but a complex, layered world of multiple, simultaneous exotic storms, each with its own unique form of precipitation. While this sounds like the stuff of science fiction, the concept is grounded in rigorous laboratory experiments. Here on Earth, scientists have used powerful lasers and diamond anvil cells to recreate, for a fleeting nanosecond, the immense pressures found deep inside ice giants. In these experiments, they have successfully taken polystyrene, a plastic similar in composition to methane, and compressed it until the carbon within it indeed formed nanodiamonds. This provides tangible, experimental proof that the physics behind diamond rain is sound. The challenge, of course, is scaling this from a microscopic sample in a lab to a planet-wide phenomenon occurring over billions of years. The very existence of this hypothesized diamond rain could also help solve other Uranian mysteries. For instance, it would act as a highly efficient mechanism for separating carbon from hydrogen, potentially explaining the surprising depletion of methane in the upper atmosphere that Voyager 2 detected. The carbon is literally being scrubbed from the sky and sequestered in the depths, leaving the upper layers with a different chemical signature than we would otherwise expect. This continuous downward transport of dense material also releases gravitational energy, which could provide a subtle, additional heat source deep within the planet, adding another variable to the complex thermal models that try to explain why Uranus is so much colder than it should be. The glittering heart of the ice giant may hold the key to understanding its frigid and quiet exterior. And so we find ourselves here at the edge of the known, having journeyed through 25 of the most profound enigmas our solar system has to offer. From the cataclysmic impact that knocked Uranus onto its side and the baffling absence of its internal heat, to the chaotic tumble of its magnetic field and the dark, narrow bands of its mysterious rings. We have wandered through an atmosphere that smells of rotten eggs and experiences 42-year-long seasons, witnessed the possibility of diamond rain deep within its interior, and stood in awe of moons like Miranda, a world scarred by unimaginable violence. We have grappled with the density paradox that sets it apart from its twin Neptune, listened to its sporadic radio whispers, and tried to comprehend the forces that drive supersonic winds across a world of profound cold. Each mystery is a thread in a tapestry of wonder, and together they paint a portrait of a planet that is not merely an object in space, but a challenge to our very understanding of how planetary systems form and evolve. Uranus is more than a distant ice giant. It is one of the final, great frontiers in our exploration of the solar system. It represents a gaping hole in our planetary knowledge, a world that has been visited only once and fleetingly by a passing probe decades ago. The puzzles it presents are not trivial curiosities. They are fundamental questions that cut to the core of planetary science. Understanding why Uranus lacks a strong internal heat source could rewrite our models of planetary formation. Decoding the secrets of its magnetic field could reveal new states of matter within its superionic ocean. Studying its extreme weather and complex moon system provides a laboratory for understanding processes that operate on exoplanets light years away. This is not just about solving the riddles of a single world. It is about piecing together the history of our entire cosmic neighborhood and our place within it. The need for a dedicated mission to Uranus has never been more urgent or more supported by the scientific community. A flagship orbiter and probe capable of spending years within the Uranian system is the essential next step to transform these mysteries into revelations. Such a mission could map the planet's gravitational and magnetic fields in exquisite detail, directly sample the composition of its atmosphere, and provide high-resolution images of its moons that would put Voyager 2's glimpse to shame. It would allow us to listen to the planet's erratic radio pulses over a full orbit, monitor its weather across multiple seasons, and finally determine the true age and composition of its enigmatic rings. This is not merely a wish list, it is a scientific imperative. The clock is ticking, and the orbital window for such a journey, using Jupiter for a gravity assist, opens soon. We must seize this opportunity to launch a new golden age of ice giant exploration. The story of Uranus is still being written, and its greatest chapters are yet to be discovered. It reminds us that our solar system is a place of infinite complexity and breathtaking beauty, where every world has a unique story to tell if we are only brave enough to go and listen. So we turn now to you. After this journey through the unknown, which of these 25 mysteries captured your imagination the most? Was it the towering cliffs of Miranda, the thought of a glittering hail of diamonds, or the unsettling silence of a missing internal heat source? Share your thoughts in the comments below. Let's continue this conversation and keep looking up together at the wonder